Permutation group. In elementary statistics, permutation, it is refers to the arrangement of objects with reference to order. Example: how many different signals can be made using the 5 flags if all the flags must be used in each signal? Answer: 5 factorial is equal to 100 different signals. In abstract algebra, let's talk about a group of permutation. So what is group of permutation? For any set A function of phi goes from A to A is called the permutation of A if phi is 1 to 1 and n to. Always remember that when we say 1 to 1, it is injective, n to is surjective, and 1 to 1 and n to was bijective. For that, I will ask a question. How can we take the set of all permutations of a set A and turn it into a group? Before we can do that, we have the set, the binary operation, and check the group operation or group's property, which is the closure, associativity, existence of identity, and existence of inverses. Let's first talk about a set. What set I am talking about? You can think that it is all about the set of A, but actually it is not about the set A, but the set of permutation on A that we gonna work out. Example: suppose set A is equal to the element of 1, 2, 3, 4, where phi goes from A to A, or bijective. So in writing the phi, the set of elements of A must be written at the top, then any number belongs to in set A, or you can write it in any order. So we can read this as phi takes 1 brings it to 2, phi takes 2 brings it to 4, phi takes 3 brings it to 3, and phi takes 4 brings it to 1. So in tau, same in phi, we can write on the top of the element is the set elements or the set of elements of A, then any number or belongs to the set of A in any order. So since there are 4 numbers, so we can written it into 4 factorial is equal to 24. So let's have the binary operation. A function of f goes from A to B and function of g goes from B to C, then the composite function of g composed of f goes from A to C is defined by g composed of f of x is equal to g of f of x for all element for x belongs to A. So let's have examples. So the same examples that we had in our set. So let's have the composition of the phi and the tau. So we can read this the first. So we can read this as phi composed with tau acting on something element of x, where x is something on the set of A. So probably it will be the 1, the 2, the 3, and the 4 is equal to phi of tau of x. So we have here, the second is the phi composed of t of 1 is equal to phi of 1 is equal to 2. So we should focus on the set of the set of the tau, and the first, which is the elements 1 2 3 4. Then below of that is 1, so first the 1, so tau takes to 1, below is or takes to brings to 1. Then before proceeding to the elements of the phi, which is 1 1, then 1, so the answer is 2 because below of the 1 is the 2. Next is the phi composed of tau of 2 is equal to phi to 2 is equal to 3. So same, so on and so forth. Then phi takes to composed of tau of 3 is equal to phi of 3 is equal to 4, and phi composed of t4 is equal to phi of 4 is equal to 1. So the composition, with the use of group of permutation using the composition or composite function, we have the answer of phi composed of t of x. So we have 1 takes to 2, 2 takes to 3, 3 takes to 4, and 4 takes to 1. We have the group properties. So we have there the theorem and the proof of the four properties, which is the closure, the associativity, the identity, and the inverses. So let's have first the theorem. If A is any non-empty set and set A is a set of permutation of A, then the set S of N forms a group under permutation multiplication. So proof is first is the closure. Permutations are bijective functions. When we say bijective, it is 1 to 1 and n2. Permutation multiplication is a composition of functions. The composition of two bijective functions is bijective. So we have that in the binary operation. Therefore, the set of permutation of A is closed under permutation multiplication. Associativity. Permutation multiplication is the composition of functions. Like we had the composite function, the composition of function is associativity. Therefore, permutation multiplication is associative. And next we have the identity, proof of identity. So let P be the permutation. Permutation defined by PO sub O of A is equal to A for all A belongs to A. Then for any permutation of phi belongs to SA or set of A, we have P sub O composed with phi is equal to phi composed of P sub O is equal to phi. Thus P of O acts as an identity element in set of A. In inverses, permutations are bijective functions. If a function is bijective, then it is invertible. Therefore, for each phi belongs to set of A, there must be a function of inverse of phi such that inverse of phi composed of phi is equal to phi composed of inverse of phi is equal to P sub O. Since the group axioms are satisfied, set A forms a group under permutation multiplication. So these are the properties of group of permutations. So the concepts of these compositions are taken some of the references from the YouTube and Google.
So this time we will discuss about. Okay, so this time I will discuss